Good morning, everyone. Welcome to the Enabling Technologies track. My name is Phil Lapsley. I'm with the Embedded Vision Alliance. I'm also with BDTI. The Enabling Technologies track is one of my favorite tracks here at the summit because it is all about products. It's all about practical products that you can, products that deal with feedback, for example. They're all about practical products for computer vision, things that you can actually buy today. You can go and see them on the Vision Technology Showcase floor. So this is where the rubber meets the road. So I'm really excited about our next set of speakers. The very first pair of talks are going to be from Xilinx. One of them is on Caffe to Zynq, state-of-the-art machine learning inference performance in less than 5 watts. And that's going to be presented by Vinod Kathail. And then the second one will be OpenCV on Zynq, which is accelerating 4K 60 dense optical flow and stereo vision. And that will be presented by Nick Nee. So everyone, if you could please keep your mobile phones turned to vibrate, that would be great. And if Vinod, if you'd like to come on up here. Vinod is a distinguished engineer from Xilinx. Prior to Xilinx, he was at Synfora. And I am just so excited to hear about this project because people say, FPGAs, oh, awesome performance, but hard to program. Vinod is about to tell us why that's not true. So thank you very much.
Yeah, thanks, Phil. Good morning, everybody. So I'm actually going to talk about how do we implement machine learning inference on Zynq SoC in a much more power efficient, much more performance efficient manner. This is the outline of my talk. I'll talk about why Zynq SoCs are really good for deep learning inference with a combination of programmable logic and ARM processors. They are really, if I was to say, they are really designed for deep learning inference in my mind. Then I'll talk about how do we go from Caffe, which is a standard machine learning framework, and how do we take the trained networks from Caffe and implement it on Zynq in seconds. So the approach that I'm going to present is really an overlay architecture-based approach, in which you really actually see only the software part. You only deal with the software part. It presents a software-like experience. You really don't deal with any of the hardware complexities of the FPGA. And then I'll close with showing a full system example where we combine machine learning inference with other parts of the computer vision, for example, functions coming from OpenCV, to build a complete multi-sensor example. There is a diverse set of applications. Over the last 2 years, the advances that have been made in the machine learning, it probably surpasses all the advances that were made over the last 40 years or 50 years, okay? There's a lot of new networks coming up. There's a lot of new application areas that are coming up. Here are some of the application areas that you can, that machine learning can be applied to. The point really is that there are diverse areas, but also they have a diverse design goals in terms of power, performance, efficiency, cost, accuracy. So it go all the way from Google Translate, which uses very large networks, to speech, to hearing aids, which uses very small networks, but the latency is very important, okay? To ADAS, where the latency is important, but also the accuracy is also important, right? Here is a brief overview of the Zynq SoC. It's like any other typical SoCs. The main point here really is that the SoC has a programmable logic that can be reconfigured to your needs, okay? And that's really the main part of the Zynq, that we will see how the programmable logic can be used to implement the machine learning inference very efficiently. Other than that, it's a standard SoC with providing ARM cores, a lot of memory bandwidth. The other thing I should mention is that there is a very high bandwidth access between the ARM cores and the programmable logic, so that you can do the data transfer between software and the hardware very efficiently. To start out, I'm going to give you some numbers, okay? So we took the Zynq SoC and compared it with an embedded GPU. in terms of both the performance per watt, that's the efficiency of implementation, as well as the latency. So the numbers that we have really are 6x better than the embedded GPU, and the details are in the part of the slide, and I'll go over them, as well as 1/5 the latency of the embedded GPU. So in terms of, if you look at GoogleNet was our the representative network that we use for benchmarking purposes. We can get 370 images per second on ZU9. On ZU5, which is another Zynq device, we can get 155 images per second. One thing that I should point out here is Xilinx actually has a wide range of devices that vary from small devices that are designed for low power to larger devices that are designed for high performance. So we just took 2 representative devices from the family, ZU9 and ZU5, and compared them with the embedded GPU. In terms of the power, on the ZU5 we are pretty lower power compared to eGPU, whereas for the Xilinx ZU9 we are close to the embedded GPU power. So if you look at the total images per second per watt, which is really the efficiency metric, we are pretty the Zynq implementations are very efficient compared to the embedded GPUs or other SoCs. The other part you should look at is also the latency. The latency in the embedded application latency is very important. So in terms of latency, our latency differential is close to 1/5 of the latency of the embedded GPU. Now, one of the things the GPUs do to get higher throughput is to what is called the batching the images, in the sense that they take multiple images and run them together through the process, right? Batching actually improves your throughput. So in the last table, you see that batching gives actually high throughput to the embedded GPU, but the result really, but the corresponding thing is really you also increase the latency. Latency significantly increases if you batch the images. So with GPUs, you can get high throughput or high latency, but you can't really get both. Okay? With FPGAs, you can actually get both. You can get high throughput as well as high latency. That's if one message that I want to take you out of this slide, that's the message that you should take out of this slide. The other part really is that the training and inference used to be together. They used to be all done on GPUs, 32 with floating point, but the training and inference are diverging right now. So you are seeing that the inference, especially in the embedded domain, where the power is actually much more important, people are moving away from 32-bit inference to 16-bit fixed point inference, 8-bit fixed point inference, and even to the lower precision like 4 bits and 2 bits. The other thing that, so here, for example, is the table from one of the papers published in the Hot Chip Symposium. If you take the network and run it with the FP32, compare the accuracy to the 8-bit accuracy, the loss in accuracy is very small. And this is actually without retraining the network. If you retrain the network, you can actually sort of capture the accuracy, the lost accuracy, and you can come pretty close to the 32-bit inference, right? The other thing really is if you look at GPUs, NVIDIA GPUs are actually moving to 8 bits. They are still now started supporting 8 bits. If you look at the Google TPU that was announced recently, they are actually using 8-bit inference. And all of this is because of conserving the power. FPGA, by nature, are actually very good at doing 16-bit, 8-bit, and even lower precision, as you will see in the later slides. Here's another slide, which is really, again, coming from a published paper by Hong and Delhi in one of the conferences. And it's showing that if you take the AlexNet, okay, 4 bits are good enough for convolutional layers. Okay, you don't really need more than 4 bits to capture the accuracy. Whereas for the fully connected layer, you actually only need 2 bits, and you can get the same amount of accuracy. Right? So the 2 point really is people are moving from higher 32-bit precision to the lower precision, 8-bit, 4-bit, and 2 bits. And the other point really is that the different layers in the network, okay, the convolution layers versus fully connected layers can be executed on a different precisions. For example, here 4-bit and 2-bit. And without loss of any accuracy. So here is where Zynq really shines. If you look at the CPUs, they can do 32-bit multiply add. Some of the CPUs also have SIMD operations so that they can do four integer operations at the same time. However, the parallelism or the number of operations that you get is really not large enough. If you look at GPU, they started with 32-bit floating point. Now they're moving to 16-bit or 8-bit integer. If you look at FPGAs are designed to do any bit precision, starting from 1 bit all the way to the 16-bit. So if you look at the Xilinx FPGA or the Zynq SoC, it has the DSP units, and you can use those DSP units to do 16-bit operations. You can also use those DSP units to do 2 8-bit operations in the same cycle. Okay, there are enough bits in the implementation so that you can use some of those bits to guard the 2 8-bits separate, 2 8-bits, so that you can keep them separate. This is something that's actually unique to Xilinx. Our competition does not have this capability to do 2 8-bits operation using the same DSP in the same cycle. Right? Once you go down to lower precision, like 4 bits, 2 bits, or 1 bit, you can use all the LUTs and all the reconfigurable logic that is there to implement the appropriate DSPs or appropriate units. You can probably do the same thing on the GPUs. On the other hand, you have to probably spin a new chip. Okay? Whereas on the FPGA, it's really a question of just reconfiguring your chip and go from 8 to 4 to 2 or 1, whatever precision you want. So you can actually sort of, that's the title of the slide, you can future-proof your machine learning architecture, right? You can use the same chip and do the 8-bit, 4-bit, or 2-bit inference. Here's another thing, binarized neural network that uses single bit precision for both weights and activations are actually one of the hot topics these days, because those are sort of the ultimate in the design. In the current technology is such that binarized neural network, if you implement them, you do lose certain amount of accuracy, but the field is progressing so fast that I believe that in a few years, using those networks, you can probably get the same amount of accuracy as you get from 32-bit or 16-bit. The important point really is that in order to implement the binarized neural network or binary neural network, you really need a very small amount of area. So if you compare the area that you need for 8-bit to what you need for 4-bit, it's about 4x less area. Compared to 4-bit to 1-bit, it's about 10x less area, right? So in the same area, you can do many more 1-bit operations than you could have done in the 8 bits, right? So these are sort of machine learning operations. To think of them as machine learning operations. Now, if you look at ZU9, even for 8-bit, it was actually giving you much better performance compared to TX2, 2.7 teraops compared to 1.5 teraops for TX2. For 1-bit, it really just explodes. You have something like 23 teraops of machine learning operations on ZU9 if you were doing binarized neural network. FPGA generally have lot many more LUTs than DSPs. So this actually benefit is really huge from an FPGA perspective than for any other SoCs that uses DSPs, kind of be it DSPs. The other part of the equation really is, if you want to implement neural network very efficiently, you need to have a lot of compute, obviously. So if you look at something like AlexNet or CNNs, all the convolution layer require a lot of compute, and FPGAs or GPUs can obviously give you a lot of compute. The other part of the part really is that there's a lot of data traffic that goes to the memory. Since there's a huge amount of convolutions being done, there's a lot of data that you need to bring back and forth from the memory. Interestingly enough, there's also a lot of data reuse, right? So for example, if you load weights, you can reuse one set of weights for doing multiple convolution. you can reuse the data that is output of one layer, okay, as an input to the other layer. So the more on-chip memory that you have, the better you're going to be in terms of the efficiency. Because going to the memory is 10x more power hungry than just accessing the on-chip memory. If you compare the Xilinx devices, in this case ZU7, to something like Tegra X1 or any of the eGPU, the amount of on-chip memory that the Xilinx devices have is close to 6 or 6x more than the Tegra X1. What that allows us to do is that you can actually do on-chip data flow, in the sense that you compute, put it on the on-chip memory, and then the next compute reads it from the on-chip memory, then always going to the main memory. On the GPU side, GPUs or CPUs, typically you always have to go to the main memory because there is a very small amount of cache or very small amount of on-chip memory that you have. The result really is much more power efficiency on the Xilinx devices compared to the embedded GPU. So Phil said that, I'm going to tell you how I made FPGAs easy to use. Until now, I was actually trying to tell you all about the benefits of the Zynq, the FPGA per se, but the general impression among the audience is that FPGAs are harder to use. So now I'm going to tell you, actually, no, it's not harder to use. You can pretty much use FPGAs very much like you use the CPUs and GPUs, especially for doing machine learning inference. So advantage of the Zynq that we discussed earlier, combined with the simplicity of usage, is the message that we are trying to bring here. So in terms of the simplifying the usage, we just announced a couple of months ago something called a revision stack, which is essentially a programming stack for embedded vision on Zynq SoCs. The stack really consists of 3 different things. One really is ready-to-use development kits. They come with boards, sensors, everything that you need from a hardware perspective. All the libraries and tools that you would need. So the main tool that we provide is SDSoC, which allows you to design the ARM plus FPGA starting from C++. You can write your application in C++, and the SDSoC will basically sort of partition it and design the entire system for you. In addition to that, we are actually providing libraries for both computer vision side, which Nick is going to cover in the next presentation. We have about 50 or so commonly used OpenCV function for which we provide optimized implementation. The other side is really an overlay architecture along with a software that allows you to implement CNNs on the FPGAs very efficiently. And then we have the integration with higher level frameworks. So in terms of the machine learning, we have integration with Caffe framework. Later on, we will have integration with other framework like TensorFlow, MXNet. On the CV side, we are planning to, in the future, we are planning to do an integration with the OpenVX framework. So here is what you have to do to run your CNN or your network on the Zynq chip. You use the standard Caffe framework to design and train your network. Output of this is going to be a prototext file, which is essentially a way of describing the topology of the network, and it's going to be some sort of trained weights, which is really describes the trained network. What we provide to you is a full overlay architecture that comes as a bit stream, okay, that you can download onto the FPGA, along with an API or a software that runs on ARM. Okay? That API will actually, you call that API in your program, and that API will take the network from the prototext file along with your trained weights, and then you can run any inference that you want. Okay? So literally using the machine inference or machine learning inference on Zynq is equivalent to compiling your code on ARM, because the rest of it is provided to you as an overlay architecture, and it's all done for you. You don't really see any hardware compilation. You don't see any hardware You compile your ARM code, give it the prototext weights and your images that you want to classify, and out comes the result. Here are some design examples from the flow that we just described. The first one is obviously the Google Net that we were using for our benchmarking purposes. The other two networks are SSD and FC and AlexNet. In the embedded vision area, these are the more useful networks, because they do something called scene segmentation, which is where you are taking a scene and segmenting it into various objects, or you are trying to sort of, for example, in this case, you're trying to detect pedestrians, right? This is the typical use cases for embedded vision area. We do pretty well in terms of both the images per second as well as the images per second per watt. So far, we have been describing how can you use Zynq for doing machine learning. In the next few slides, I'm actually going to describe how do we take machine learning as implemented on Zynq and combine with other parts of your embedded vision design. Because a full real life example is not just going to have machine learning, it's going to have other components also in a design. For example, it will have some sort of video input. You might have other imaging functions, other vision functions. And that's actually, in order to build the entire design, you can configure the overlay architecture that we provide using the system optimizing compiler. You can sort of vary the size of the overlay architecture. You can tell, I want to use only these many DSPs, these many VRAMs, these many LUTs, and then you can sort of configure the architecture to fit those parameters. And once you have configured that architecture, then essentially it looks very much like the previous slide that I showed you. You can give it a prototext file and train weights and do the inference. In addition to that, we use the standard SDSOC way of doing things, which is essentially you describe your application in C++, you profile the application to find out where the hottest spots are, and then you tell the compiler that you want to move these particular functions in the hardware. So you can have your application that uses part of the OpenCV functions, part of the vision functions, part of the video functions, and then you have the machine learning that's sort of together. The vision functions will get compiled using the system optimizing compiler, the machine learning, and then it will get integrated with the configured overlay architecture for machine learning, and then the system will generate the bit stream, and you can pretty much build the entire system, which actually I'm going to show you in the next slide. So here is a system which actually combines three different things, which are very important from a embedded vision perspective. One is support for multiple sensors, sensor fusion, and I'll tell you what they are. The OpenCV or computer vision like functions, and the CNN for doing the machine learning. So this example actually takes a stereo camera as an input, does the stereo vision to do the depth calculation, which is actually shown here. It actually takes a standard high quality camera, passes it through the standard ISP chain, and then does the optical flow, which is another vision function for doing the motion detection. And then the CNN in this case is actually an FC and AlexNet that is driven by the recorded video to do the pedestrian detection. And all these things are then sort of put together into a frame buffer so that you can see all the outputs in the single image. So summary, Zynq SoCs offer superior performance, lower latency compared to other SoC offerings. I hope I convinced you of that by the numbers that we had. Part of the sort of a general thing about FPGAs is that it's really hard. They are really hard to use. Revision Stack provide the seamless inference of custom deep learning networks from Caffe to Zynq SoCs. They will be available publicly at the end of the May timeframe, and you can visit Xilinx revision for more information. We will also have a booth in the technology showcase where you can actually see the demo in action. And there are the other resources. Any questions?
Thanks for the talk. I have a question regarding the integer accuracy. Looks like from the previous slides, the VGG16, the accuracy is really low. I'm wondering, so why? Yeah. Can you? Yeah, this here. It's only like a fixed integer 8. It's only 86.4. I guess that's top 5, right?
Compared to the IP32 is
even IP32 is surprisingly low. That's 86.6.
okay. So these are the numbers from the hot chest paper that was published by Song and Delhi about a year ago. So it's quite possible that the accuracy of the VGG has increased even further from what the numbers that they have published.
I don't think so. So easily from my experiences, like a integer 8 without any retraining, it easily can reach 90%. It shouldn't be that low.
This is the top 5 accuracy that we just got
from the top 5 accuracy
from the paper.
Okay.
Right.
Even the Google Night, that's also low. So I'm wondering, so is there something, just the evaluation system, or what's the framework?
I'll have to basically go back and check the paper, why they are quoting such low numbers.
I see. The second question is about the revision stack.
Yeah.
It looks like it has to go through the compilation from the network export. You have to compile the code so that before running on the FPGA system. Why is that necessary? Because if just weight and topology, it doesn't have to to compile.
That's a good question. Actually, that's by the way, that's a very good comment. So we can provide you with a fully sort of compiled binary that you can then use. So literally, we give you binary along with the overlay architecture, and then you can use it. You really don't need to do anything, right? But typically, what we find is that when you are using these networks, you also want to do something additional. For example, you're reading the picture or reading the image on ARM, and then feeding the image into this network, right? So from that perspective, we also provide you with an API that you can call in your ARM code. And if you use that API, then you have to compile the code. So both of them are possible. We can give you a fully baked binary plus bit stream, and you just call the binary with the prototext, weights, and your inference image. Or we can give you an API that you can use in your larger program and then compile the program.
Both available in revision,
yes.
the library
Yes.
or the SDK already.
Yes.
Okay, got you.
Or
Thanks.
rather in May.
Okay, thanks.
Multiple questions.
Hello, I have a question regarding the conversion from floating to fixed point. You talked about how you go automatically from Caffe to FPGAs. Caffe is in floating point, and then you're going to do it in 8-bit integer. How do you do that conversion, and is that done automatically? And how do you do the dynamic range management when you go to 8-bit precision?
Right. If you want, the approach that we suggest is a two-phased approach. Okay. The first phase is really we provide you with certain scripts that you can use to convert the 32 to basically quantize the 32-bit bits into 8-bit bits. Okay, that's a kind of a evaluation approach in the sense of you just do the conversion, run your network, see the accuracy, right? If you lose the accuracy too much, then we actually suggest that you use a Strato Caffe, okay, to sort of adjust the weight and retrain your network, because this Strato actually provide you a 8-bit, the lower precision training that you can use. So it's a kind of a two-phase approach.
Hi, I have two questions. So first you mentioned like you have a 53 core in your SoC. Like I would like to know like what's the performance and the frequency, for example, when you design the A53 core, and will that be the bottleneck of your SoC? And second question is that also you mentioned like you have on-chip memory for like 38 megabyte. Like if you do OpenCV and like those image processing like algorithms, will that also be a bottleneck for your system? Because if you're doing like, I'm not sure like how large is your image that you're going to process on your SoC, but if you're talking about like 12 megapixels and things like that, it will be much larger than your designed memory limit. Yeah, thanks.
So I think I don't have the spec handy, but I think the A53 runs at about 1.2, 1.5, up to 1.5 gigahertz. That's the operating frequency for A53. There are actually 4 A53 in the Zynq, right? So it's not just one. So we have never really found A53s to be the bottleneck in terms of the design. So that's really never the issue. In terms of the on-chip memory, you're right. If you have like a 4K camera, 4K 60, or I mean multi-megapixel camera, you really can't put the entire image into on-chip memory. And typically, what people would do in order to process those images is basically they will block the image. They will partition the image into multiple sub-images, and they will do the processing on sub-images, which then you can actually locally store in the memory. How many more questions? One more?
Zero.
Zero? Okay.
But
by the way, I'm available, so if you have any questions, just catch me outside and we can talk.
I was just going to say that the great news is that there's tons of opportunity to interact with Vinod and Nick and the other exhibitors here on the show floor. So thank you very much.